Section 11.5, surface area again, but this time of pyramids and cones. Difference between a pyramid and a prism. Take a look at this pyramid. Our prisms had always rectangles around for their lateral faces, all rectangles, and the triangles were on the bases. On the pyramid, you have triangles for your lateral faces, and the base is only on the bottom, not on the top. So they're not going to end up being the same as far as our formulas go, but close. Definitions first. Pyramid, the base has to be a polygon. Doesn't have to be regular, but most of the time they will be. So it can be a square, triangle, octagon, hexagon. The lateral faces, as I just showed you, are all triangles. And they have a common vertex, which means they're all going to come to a point at the top. Common vertex. Take the time to pause this and write these down. Altitude is the height from the vertex to the base, but it has to be perpendicular. If I take a look at this pyramid that you see here, okay, the height of this pyramid is not measured along the side of it like this. It's just a matter of how tall is it from top to bottom, measured on a perpendicular. So if I could, I'd take maybe straight up through the middle and say, well, how tall is that? Oops, at a perpendicular. You want to make it perpendicular though. Or you can measure it out here. But if you measure it out here, it's got to be perpendicular. You cannot slant it. So that is the height, or in other words, altitude of a pyramid. But then there's something called the slant height. We didn't have that on a prism because a prism wasn't slanted. A slant height, and this is a italicized or like a cursive L with a loop in it, is how you have to print that or write it. It's the altitude of just one of the faces. So the height of just one of the faces. So if I look back at this the way I had it, as you see here, how tall is this face? Or how tall is this face? If it's regular, they'll be the same size. So now you are actually measuring it on a slant because it's called the slant height. What's the difference? This one's going to be a little bit longer than this one is. Think of it in terms of a right triangle. This would be more like a hypotenuse, and this is going to be straight up and down. So a slant height is just one face, and altitude is the height of the whole thing. Going to be very important that you know that vocabulary so that you do your formulas correct. A regular polygon, the base, or a regular pyramid, the base is a regular polygon. Perfect square, perfect equilateral triangle, perfect hexagon, whatever it is. All right. So let's do a little work with that. Hopefully you don't have to draw this because you have a handout. You have a right square pyramid. Since it's called a square pyramid, you know that this base is square, which means it's a 30 by 30 square. The height of it is 20 inches. So that's how tall it is from top to bottom. It's 20 inches from the bottom of the pyramid to the top of the pyramid if you measure it straight up. Or you could put it right smack through the middle of the pyramid. From vertex to the center of the base, that height is 20 inches. They want to know how big is the slant height. How big is the slant height if we know that this is 20? Well, here's how this is going to work. The only way we can find the slant height, we can use the face of any triangle, but I'm going to use this one on the side here because it's easier to see. We're looking for this slant height over here. To find that slant height, we are going to use the height that was given straight up through the middle. The distance that we know straight across here was 30, but if this lands smack dab in the middle of the base, it's only 15. So we can make right triangles, if I can show you here, out of, here's my altitude, or my height, that's 20. Here's my slant height over here. That's what I'm looking for, and I need to make a right triangle out of it. How do I make a right triangle out of it? I can go this distance, which is half the base. Obviously not the whole pen. You're going to stop right here. So half of the base, you've got the height, and now that just turns into the Pythagorean theorem. 15 squared plus 20 squared equals L squared. Do the math, and you get 625, which is a very nice, perfect square number, so that when you're looking for the slant height, you find out that it is 25. Same units, we're going inches. Okay, once you know the slant height, it now says find the area of one of its lateral faces. Just one of its lateral faces. Instead of working up here with this whole three-dimensional pyramid figure, you know that its lateral faces are triangles. Not necessarily equilateral triangles. Okay, this whole base is square, but it doesn't mean that these are perfectly all the same size. You know that it's isosceles because it's regular, but you don't know how long this base is compared to this height. What you do know is that this was 30 inches. And you just found the slant height. You found this distance up here. We found it on the side, but they're going to be the same no matter where you draw it. So you did just find the slant height that went right up through the middle, which is nice. And that was 25 inches. Since it goes perfectly straight up through the middle, it makes a right angle. Why do we need a right angle? Because area of a triangle is half base times height. And to find the area of a triangle, we need half the base, 15, times the height, 25. I did it like this, half base times height, which is the way I was doing it on the prisms. 15 times 25, just to double check, is 375. Square inches for the area of one of its lateral faces. So how are we going to find the surface area of a whole pyramid? I'm not giving you a formula. You could go look it up if you wanted to. You could go look up, try to cheat, try to go on Google, try to get some answers other than this way to do it, and it'll tell you that the surface of a pyramid is capital B plus 1/2 PL. And you'll look at that and be like, what? Look it up, it's in the book. But doesn't it make more sense? Just find the area. It's faster even, and it's just more common sense. Find the areas of each face and its base. We need 4 triangles and a square. If it's a hexagon, we need 6 triangles and a hexagon. So if we want to find the surface area of the pyramid above, we know that we need 1 base, and in this case it was a square, and we need 4 triangles. A base and 4 triangles. The square was a 30 by 30 square, and the 4 triangles, we just found out, you better put 4, we just found out that each triangle was 375 inches squared. Multiply that out all at once. 30 squared, 30 times 30 plus 4 times 375. And you find out that the surface area of this pyramid is 2,400 square inches. Okay, next up. What if you have a regular hexagonal pyramid? I dare you to draw a regular hexagonal pyramid. You don't have to. Its side is 9 centimeters. Its slant height is 8. Okay, so we know to find the surface area, we're going to need 1 hexagon plus 6 triangles. 1 hexagon, which is the base, and 6 triangles. We already worked with solving and finding areas of hexagons. Again, you don't have to draw the entire hexagon. You just have to find one of the triangles and multiply it times 6. It said the sides of this regular hexagonal pyramid is 9. So I'll put 9 here. We know to find the area of a triangle, we need 1/2 base times height, and we're going to have to multiply it times 6 because there are 6 of those in a hexagon. So let's cut it in half. I'm going to move that 9 over, and we'll make this 4.5. So half the base is 4.5 times the height. We're getting good at 30, 60, 90 triangles, hopefully. Height is 4.5 square root of 3 times the number of sides. There are 6 sides in a hexagon. So we just found the base of our pyramid. We have to add to that the 6 triangles that are going all the way around. Not the same triangles as this. Okay, not the same triangles. This is the base. And it was split up into 6 different triangles. The triangles going around the outside are these. They're not the same size as the triangles in the hexagon. We got to find all 6 of those. So we have to do 6 triangles at 1/2 base times height of each one of those triangles. Let's think about this height for a second. The height of this triangle, if I go back up and look at my other pyramid, the height of a face is a slant height. You don't think vocabulary is important? If you're looking for it, the altitude of a face, we're trying to find the face. So this H is really the slant height. So we're going to take 6 times 1/2 the base, and I'll draw a new triangle. The bases of these are still the same size as the bases of your hexagon, 9. So 1/2 of our base is 4.5, but our slant height, they actually gave it to us. That was super nice. We didn't have to try to do Pythagorean theorem and calculate it out. So there's 1/2 base times height of the hexagon and 6 of those. There's 1/2 base times height of a face and 6 of those. I'm not going to make you do this as an exact answer. We're just going to go straight into the approximate. Start typing, not piece by piece. It all goes in at once. 4.5 times 4.5 times square root of 3 times 6. Don't forget your parenthesis if you need it there. Plus 6 times 4.5 times 8 equals 426.44. Half the base times the height times 6 plus 6 times the triangles. 426.4 square centimeters. Okay, yeah, you don't have to draw all that, but let me just give you a quick. There was my hexagon. I'm going to actually move it down a little bit. Here's my point at the top. Draw your pyramid. I make it look easy, but maybe if you did this for 23 years, you'd be able to draw a pyramid too. So first, we found the triangle of this hexagon, which was here, and multiplied it times 6, because there were 6 of those. One base. Then, we found the area of this triangle using same thing. Half the base was 4.5 because each side was 9. And they gave us the slant height. In this case, the slant height was 8. So we got to just do half base times height. And there were 1, 2, 3, 4, 5, 6 of those triangles surrounding it. Let's switch to a cone, a lot easier. When looking at this cone, it's related to a pyramid, but it's not polygons. We have a circle instead of a polygon, and we don't have any triangles around the cone. No triangles around the cone. So, what does that formula look like? Pi r squared, that gets us our circle, base, plus pi times radius times slant height. Slant height on a cone, same difference. If you measure the height of the cone, you're measuring it from here to here. If you measure the slant height of the cone, you're measuring it along the side. Slant height of the cone. Height of the cone. Slant height of the cone. Okay, how do we do that? The circle plus pi RL. Take a look at this diagram. We're going to do surface area of a cone equals area of the base, pi r squared, plus pi RL, which gives you the rest of the cone. Pi times 4 squared is 16 pi. Always put the 16 first. Plus pi times 4 times, no slant height. They gave us the height. Don't use that. Slant height's going to be a little bit longer. But they also gave us enough information to find the slant height. A squared plus b squared equals c squared. No rounding. No rounding. Not yet. 4 squared plus 6 squared is 52. C squared is 52, which means C is the square root of 52. I should have put L, really, slant height. Our slant height is the square root of 52. So what does that mean for our surface area? It means you're going to take 16 pi plus 4 times pi times the square root of 52. This would be the exact answer. That's totally ugly. Let's just go to the nearest tenth and round that all out. 16 pi plus 4 times pi times square root of 52, which is 140.9 units squared. So is a cone easier than a pyramid? Probably, because you're not going to have a whole bunch of different shapes for its base, and you're not going to change the number of triangles around the outside. So yes, it's much easier. You just got to make sure you can work with pi and the Pythagorean theorem. All right, that's it for notes 11.5.